AI data centers were designed for 99.999% availability. 5 nines. That is the number in the contracts. Some of the newest facilities are running at 80. Not 98, not 95, 80. A gap like that is not a rounding error. It is the difference between a data center that prints money and one that burns it. In Memphis, xAI's Colossus facility runs on gas turbines. Those turbines developed cracks. In the United Kingdom, more turbines cracked. The batteries installed to smooth out power delivery are dying in weeks or months, hardware built to last years. In August, the North American Electric Reliability Corporation did something it rarely does. It issued a Level 3 alert, the highest severity tier, asking data center operators to disclose how their facilities actually behave on the grid. Last September, NERC found that load models failed for 3/4 of the 33 gigawatts of data centers already in operation. The grid does not know what these facilities will do next, neither do the people who built them. I have sat in due diligence rooms where availability assumptions were the first thing we stress tested. A 1-point miss on uptime used to be a rounding issue. A 20-point miss is a broken thesis. So here's the question this episode answers. The failure is not about how much power exists. It is about the quality of every electron. Who owns the fix? Here is what makes AI loads different from anything the grid has carried before. They do not ramp, they spike. Drew Baglino, former Tesla executive now running Heron Power, describes it this way. A 1 gigawatt AI facility can instantaneously exceed its design load by 50%. 1 gigawatt becomes 1.5 gigawatts in a blink. Shannon Miller, CEO of Mainspring Energy, puts it in city terms. A single gigawatt scale campus is like half of Boston flickering on and off every few seconds. John Perella of TerraFlow Energy has the best analogy. A traditional data center cruises like a car in 6th gear. An AI facility drops from 6th to 1st and back, constantly at full highway speed. Now follow the damage downstream. Jennifer Scanlon, CEO of UL Solutions, points to arc flash events, power surges violent enough to destroy chips. Schneider Electric's Shremant Roy tracks subsynchronous oscillations, grid vibrations that traditional protection systems were never designed to catch. The batteries absorbing these shocks wear out in weeks. The gas turbines compensating for them crack. This is not an energy shortage. Texas and the Midwest have campuses above 5 gigawatts in development, roughly the electricity consumption of New York City. The electrons exist. What does not exist is delivery clean enough for silicon that reacts in milliseconds. The industry spent 3 years asking how many gigawatts AI needs. The better question was always what those gigawatts look like when they arrive. Jason Hoffman, a veteran of data center operator Switch, prices the downtime. A single minute offline at a large AI facility runs from thousands of dollars to several $100,000. Multiply that across facilities running at 80% of contracted availability. Now look at the biggest single project caught in this. In West Texas, Julant and Chevron are building a 267 gigawatt campus. The anchor tenant is Microsoft. The contract requires 99.999% availability. The campus was supposed to come online in 2027. It has been pushed to 2028. CEO Chris James confirmed the delay. A year of delay on a 267 gigawatt campus is not a construction slip. It is billions of dollars of contracted revenue moving 12 months to the right because 5 nines turned out to be a physics problem, not a procurement problem. When the grid's own load models fail for 3/4 of the fleet, no operator can promise availability it cannot predict. 5 nines stops being an engineering target and becomes a negotiating position. And this is where the feedback loop tightens. GPU clusters that cannot hold availability cannot hold customers. Customers who cannot hold availability stop ordering GPUs. Every hyperscaler earnings call this year has celebrated the CapEx number. For hyperscalers, $725 billion of AI infrastructure committed for 2026, up 77% year over year. Almost nobody is pricing the reliability of what that CapEx buys. Spending is not capacity. Capacity is not availability. The market is valuing the first number and ignoring the third. Now watch what the most important company in the chain is doing, not saying, doing. NVIDIA's Dion Harris confirmed that, starting with Blackwell in 2024, the company began working directly with power equipment specialists. Heron Power, Drew Baglino's firm, is developing load fluctuation management hardware for NVIDIA's 2027 server generation. That is the chipmaker redesigning its roadmap around the grid's weakness. Then, this month, NVIDIA invested $3 billion in Lancium, $2 billion upfront for roughly 20% of the company, another $1 billion tied to milestones that could take the stake to 30%. Lancium is a Houston-based power and data center developer valued around $10 billion. It has 4 gigawatts signed and a 15-gigawatt pipeline. Its Abilene, Texas site, 1.2 gigawatts approved by ERCOT, is the first Stargate campus. 8 buildings, 50,000 GB 200 NVL72 systems per building. A second site in Childress, Texas, another gigawatt, breaks ground this quarter. Zoom out and the pattern gets louder. In a single quarter, NVIDIA deployed $18.6 billion across the AI infrastructure stack. CoreWeave, Nebius, Lumentum, Coherent, Marvell, Commonwealth Fusion, TerraPower, chips, optics, nuclear, fusion. And its vendor financing commitments to customers buying its own hardware now total roughly $600 billion. Amazon made the same logic visible from the other side. On August 7, it confirmed a gas plant at its Texas GW ranch, 35 turbines, 7.65 gigawatts, off-grid, feeding data centers directly. The seller of the picks is buying the mine. NVIDIA is not diversifying, it is defending demand. If availability breaks, GPU orders break. Owning the power position is how you protect the chip position. The bottleneck moved, and the smartest balance sheet in the industry moved with it. China is hitting the same wall. It is entering from the other end. This year, power compute coordination was written into the government work report for the first time. In May, 4 ministries issued a joint action plan for AI and energy integration, targeting gigawatt-scale compute facilities co-built with their own energy systems. New data centers at national hub nodes are required to run on more than 80% green power. The mechanics are already running. In Ulaanbaatar, Inner Mongolia, the country's first integrated wind-solar storage project feeding a data center directly came online in July 2025. 30,000 kilowatts of dedicated generation, 848 million kilowatt-hours of self-consumed green power a year. In Horinger, a dispatch platform samples wind and solar output in milliseconds and moves compute load to match, charging storage when generation peaks, drawing it down when it dips. Across Gansu and Ningxia, aggregation pilots and dedicated lines are already bypassing the public grid to feed cloud bases directly. And on August 6th, Envision powered up what it calls the world's largest single AI computing facility in Ulaanbaatar. 2 gigawatts of planned capacity, built in reverse order. The wind farms and storage came first. The data center came after. In July, Jipu AI powered up a 1 gigawatt data center in Inner Mongolia running entirely on domestic chips. Not a single NVIDIA GPU inside. The power came first there too. Envision built a power plant before the data center. NVIDIA is buying the power plant after the data center. Same destination, opposite directions. Notice the structural difference. The American fixes we just covered manage volatility at the device. Batteries, turbines, voltage hardware at the server hall. The Chinese approach manages volatility at the source, generation, storage, and compute dispatched as one system before the fluctuation ever reaches a rack. Neither entry point is finished. Device-level fixes depend on hardware that does not fully exist yet. Source-level integration depends on geography and coordination that most markets cannot replicate. But both confirm the same thing. The constraint on AI is no longer silicon and no longer energy volume. It is the stability of the flow between them. Last episode, we looked at orbital compute, AI infrastructure escaping the grid entirely. This episode is the ground-level view of the same wall. Before compute can leave the grid, it has to survive the grid. Right now, at 80% availability against a 99.999% promise, survival is not guaranteed. Here is what I keep coming back to. 3 years ago, the scarce asset was GPUs. Then it was gigawatts. Now it is stability. Each time the bottleneck moved, the returns moved with it to whoever owned the new constraint. The GPU owner became the power buyer. The power buyer is becoming the utility. The companies collecting the next round of returns will be the ones holding the fix, whether that fix is a voltage device in Texas or a wind farm in Inner Mongolia.
Hardware gets the highlights. The holder of the bottleneck gets the return. Drop a comment. Does the reliability wall getting fixed at the device level or at the source? I read everyone. If this reframed how you see AI infrastructure investing, subscribe and hit a bell. New episode every week. Next episode, a Chinese AI lab with $300 million in annual recurring revenue, a model ranked first on the Arena leaderboard, and a Hong Kong IPO feeding due before the end of September. Kimi. We look at what the feeding window tells us about exit architecture for Chinese AI. See you next time.